Okay, so let's begin. So today's lecture or class will be about not Thevenin's theorem, but rather torque slip characteristics. Last week we talked about the power relationship of power and torque. So today we are extending that. This is the second part of our discussion on power and torque. Let me check we have that. Okay. Some few settings. All right, we can continue. So today we will be talking about, as I've said, the second part of the power and torque. So our objectives is we want to look at the torque slip characteristics. And also we want to look at the maximum torque that a three-phase induction motor can achieve. Okay. So those are the two objectives of our lecture today. Torque slip characteristics. A characteristic, of course, is the graph of the performance, whereby we will map torque against slip. Practically speaking, it will be torque against speed, but we'll get there. Okay. So before we start that, we will do a brief review of Thevenin's theorem, because Thevenin's theorem, we make use of it in today's lecture. Let me admit somebody else. Okay. Robert Nakitare. Okay. So today's lecture will continue with an introduction to the Thevenin's theorem. So we will recall from our circuit and network theory, or you call it electrical circuit theory, we had Thevenin's theorem and Norton's theorem. So today we'll make use of Thevenin's theorem, which will look a bit like that. Okay. Now, when we look at the, the equivalent circuit for the induction motor, we had on the stator side, we had R1 and X1, okay, which we have let them be represented here. Let's call that Z1. At the same time, within the stator, we had some elements in the core, which were R core and X magnetizing. So let's call that Z2 here. And then let's now assume, for purposes of this demonstration, that this is the load, which is our R2 over S and our X2, okay, which are on this side of the equivalent circuit. So now, looking at that side of the equivalent circuit, let us assume we are looking at these points. We have point A and point B, right? What happens with the circuit when you look at it from the point of view of point A and point B, right? We have a current I1. We also have a current I2 and a current M. Now, looking at it from this point of view, all right, if we are looking at the circuit from the load side looking towards the supply side, what Thevenin's theorem indicates or provides is that you have a voltage, a Thevenin voltage, and you have a Thevenin impedance, which are supplying your load. Yeah. Okay. Your load is supplied at that end, and this is our point A and point B, looking inwards. All right. From the point of view of the load, okay, we only see that current I2 is coming from the supply side. Whatever is on this side, the Thevenin voltage and the Thevenin impedance, represent what we are talking about. Remember that we are looking at it from that point. Okay, so actually within here, this is I2, not I1. I1 stops here. Okay, so I2 is on that point, right? Now, bearing that in mind, we would now go and find what is this Thevenin impedance and what is this Thevenin voltage. For us to get the Thevenin impedance, let's start with that. Z Thevenin, what we do is we short circuit the voltage, in which case, if we were to short circuit this voltage and we are looking at it from that point of view, the circuit would now look like this. Okay, in which case you have a Z1 there and a Z2 there, and we want to have it being equivalent to something, being equivalent to whatever is seen from point A and B. Therefore, it would be, from this point, it appears that Z1 is parallel to Z2, which is given by, of course, the product rule, Z1, Z2 over Z1 plus Z2, okay? Similarly, we can look for our Thevenin voltage. Now, in order for us to get our Thevenin voltage, we can slightly relook at how this circuit appears, right? So if we were to rearrange it slightly, so initially it looks like that. Okay, whereby we have across here, we have our, we have our Thevenin voltage looking once again through point A and B, and it is supplied by our voltage there. We have Z1 and Z2, okay? This we can redraw. We don't do anything at all to the circuit. However, we can redraw it so that it looks like a familiar kind of circuit that we are used to. Whereby we have Z1 over there and Z2 below. Now, if we rearrange it like this, it's exactly the same circuit, but we have point A and B over there. And if we rearrange it like this, it will look like what we have called before voltage divider. Yeah? And when we have a voltage divider, what do? We say that that voltage, V Thevenin, is a ratio of V1 that looks like that. So the voltage across this point is split by the voltage divider in that ratio, okay? So we have these two expressions that we will make use of later on, okay? So Z Thevenin is looking like that, right? So quick review on that. So if we want our Z Thevenin is there, and it is given by that, and our V Thevenin is given by that. Now, this is the kind of circuit that we look for. So now let's look at what we have in terms of our own equivalent circuit that we had last time. So let's redraw our equivalent circuit that we were looking at, we've been looking at since we started. Okay, so this should be very familiar by now. We have R1, JX1, R core, JXM, and then this side we have JX2 and R2 over S. Okay. Now, in order for us to kind of look into the torque characteristics, I will do something here that simplifies the circuit slightly. So the core losses, it is customary for us to assume that they have been transferred across to the stator side and they are lumped together with the windage and friction losses. I'll explain a bit about that in the next lecture, but for now we can assume that this arm is equivalent to an open circuit. That is, the core resistance is high enough that we can assume that there is nothing on this side, and we simply have JXM, the magnetizing reactance. That's our phase voltage there, our current there, IM, and similarly, let's take point A and point B, looking at it from this point, A and B. Okay, so we kind of split the circuit into two, and we assume that this is our load side and the other side is our supply side, or the Thevenin voltage side. And that would mean that at this point, I2 is the equivalent of our current supplied by our Thevenin voltage, right? Now, some reminders of some of the items that we had talked about, or the elements that we had talked about. Recall that each of the elements represented an item in itself, okay? So we had this particular element had been represented by the air gap power, or rather it represented the air gap power. And it is equivalent to 3 times I2 squared R2 over S. This one we need to bear in mind. Yeah, it becomes useful in a couple of minutes, in a short while. Okay, and we are talking about torque in its relationship to slip. So let's start introducing what is our torque being represented. So let's start looking at what are the elements that represent torque. Okay, now this implies to us that if we know the value of air gap power, we can know the value of the induced torque. Remember, the induced torque is the torque that is available at the rotor point. It's not yet converted, but it is available. It has crossed over from the stator to the rotor. Similarly, we know synchronous speed because that is directly proportional to the frequency of the voltage supply. So if we know air gap power, we will be able to know induced torque, and probably we will be able to know what is the mechanical torque. So let's look at a few of these elements that we were looking at. We've just talked about the Thevenin theorem and the equivalence, right? So for purposes of that, let's introduce a small notation here, whereby we call this Z1. Okay, so Z1 will be equal to R1 plus JX1. Just a second, let me admit somebody else. Kulo Francis, okay. Okay, So we have that Z1 as represented by the stator, essentially the stator elements that we had here. Okay. Now, what does this mean? Looking at our equivalent, our Thevenin equivalent circuit that we have here, it is very similar to what we are looking at on this side. All right, you have a Z1 and a Z2. This XM can be equivalent to a Z2. And we had, we were looking at it through point A and B, which is identical to what we are looking at on this side. And we can be able to therefore convert those elements that we have here into Z Thevenin and V Thevenin. We can be able to obtain those from looking at the circuit from that point of view. So let's start with obtaining, let's obtain our Thevenin resistance and reactance. Okay. Okay. So we use Thevenin's theorem and we look into section AB. And when we look at it from that point of view, we will say we have Z1 parallel to Z2. And this is equivalent to R1 plus JX1 being parallel to JXM, right? This is parallel to that. Z2 and Z1 are parallel to that. Therefore, looking at that, we can say if we want Thevenin equivalent of the induction motor circuit, especially the stator side, it will be product of a sum which is denoted by that. Okay. Right. And incidentally, as we will see later on, but you can, if we were looking at kind of estimations of what we would be getting, we can represent it as is equal to R Thevenin plus JX Thevenin. Okay. We can be able to separate out the real and the reactive components of this expression into two different components, which are Thevenin resistance and a Thevenin reactance. Now, algebraically, they tend to be, it's a bit complex to derive, so I won't go into it here. However, if you have the exact one, which we will see in the example, R Thevenin works out to almost exactly xm over x1 plus xm squared, and our x Thevenin less exactly works into x1. However, those are for purposes of estimation. Let me get somebody else in. Kipto Festus. Okay. Right. So we have our Thevenin resistance and our Thevenin reactance. Similarly, the Thevenin voltage can also be calculated or can also be derived. Let's look at it there. So we were saying the Thevenin voltage from the description we had done, the derivation we had done on this side, we look at the Thevenin voltage from that point of view, whereby we say that there's a voltage divider principle, whereby it's the product over the sum. So the products we are looking at, which is the Z1 plus Z2 over, no, sorry, this is not product over sum. This is voltage divider, which is the voltage itself times the ratio of that arm plus the other arm. I think I may have skipped a step, but I think have we been able to get how this is? I've just combined the imaginary elements, the reactive elements together, which are these two, yeah? So it is this plus this plus this, and we are looking at the ratio of that, okay? So these two formulas, or these two equations, represent for us our key expressions that we will be looking at. So those two are our key expressions that will allow us now to convert our circuit to look like, let me redraw it, how it will look. So it will look okay, where we have our Thevenin, JX Thevenin, JX2, our A is there and our B is there. And we finally have our R2 over S, okay? So we've slightly simplified the two. Now, remember at this point, we have our current I2 coming in. That means we are able, if we know the Thevenin and the Thevenin voltage, resistance, and reactance, the same current is flowing through all the elements of our new equivalent circuit as per what is there. This in turn means that we can get I2, which will be equal to the voltage over the sum of all the impedances that are there, which are R Thevenin plus JX Thevenin plus JX2 plus R2 over S, okay? Now, if we want to get the magnitude of the same, we would be able to modify it even further, and you would get the squares, the square root of the squares of the real elements plus the imaginary or reactive elements. Okay, and that would give us I2, right? Now, recall we had said that we have our air gap power, which we need in order to get our induced voltage, induced torque. We have it expressed, expressed like this, okay? And we have now found an expression that gives us our current that we were looking for. We already had R2 over S, and we want this current that we are looking for. Okay, so let's substitute I2 into that equation, which is 3I2 squared R2 over S, which then becomes 3 times V Thevenin over all of that times R2 over S. Okay, and this becomes one of yet another of these key expressions that we are talking about that we will need to keep an eye on as one of the key expressions that we'll work with. And because now we have gotten our air gap power, we can still therefore use our induced power formula. Yes?
Excuse me, sir. I thought the I2 was squared.
Just a second.
But you just replaced it as I2.
Ah, okay. Sorry.
Yes.
Yes. Actually, we have left a step. So it is actually squared. In fact, it's good you've raised that. So we need to square it, whereby we've skipped a step. Let's square it. So this now becomes PAG equals 3 times V Thevenin squared over, so if we square it, we remove the square root sign there, so it becomes R Thevenin plus R2 over S squared plus X Thevenin plus X2 squared. Okay, times, but we can bring it up here, times R2 over S. All of this can be brought up there. Okay. So that actually becomes our formula. And in fact, when we are looking at air gap power, we will then say 3V Thevenin squared R2 over S. This is S, not 2. Over synchronous rotational speed times R Thevenin. Make it a bit clearer. Plus in the reactive parts. Okay. So this is now actually an expression for the induced torque that we were aiming for, all right? And you will note that this expression actually has, and do that highlighting so that we can all see. This expression actually has the two things that we were talking about. We wanted to see induced torque in terms of speed, but there is no real component of speed, yeah, because there's no variable of speed. This synchronous speed is a fixed speed, it's not a variable. Actually, the speed we are looking at is represented by those slips over there, okay? Those values of slip are directly proportional to the speed that we were talking about. Remember that slip is given by ns minus n over ns, okay? So this is fixed, and therefore the only variable is the actual mechanical speed. So slip is a good representation of speed. Okay, okay, so now we have said that we have now given torque in terms of speed or slip. So what does that mean for us? It means that we can now relate the two together, which was the objective of our class today. So let's look at the torque speed characteristic. If you map out the formula that we have given there, it gives you, let me zoom in so this will fit. It gives you this representation of the two related to each other. So you can see we are looking at mechanical speed below here, but this was represented by slip, okay, in the formula. And of course, induced torque is given on that end. Now, induced torque is usually represented in relation to, excuse me, let me take a sip of water. So I was saying induced torque is represented in terms of the percentage of full load torque, right? Whereby full load torque is the rated torque that we have when you are looking at the machine itself. So let's look at some of the interesting aspects of this graph or this characteristic. You will be seeing this characteristic across all induction motors. Even when we get to single phase motors, most of them will have this, whereby you have an initial starting torque which rises to a peak, which we call pull out or maximum, and then drops down to 0. Remember the relationship of the speed and the synchronous speed and how it affects torque, right? So at this particular point, we have our synchronous speed. At this point, let me change that color. At that point, we have the speed or the slip, sorry, is equal to 0. What does that mean? Remember when we were talking about the rotating magnetic field, we said that if for any reason the rotor catches up with the synchronous speed, the rotating magnetic field, if it reaches synchronous speed, whereby the rotor is moving at the same speed as the rotating magnetic field, there is no relative motion between the two. And the principle of operation depends on there being relative motion between the actual rotor and the rotating magnetic field. So at this point, we have slip being equal to 0. So the difference between the two is 0. And correspondingly, we note that the induced torque, the value of induced torque is at 0. Okay? So slip is at 0, speed is equal to synchronous speed, and the induced torque is 0. It has dropped down to 0. Okay? The second element that we would want to look at is this section. That section is the normal operating region. Remember when we spoke of at the beginning, we said that slip is usually a very small figure, and we gave, I think we said between 2 to 5% slip. Now, this region, if you notice, the curve itself is almost linear. It tends to be linear. That means that within this region, you can expect that the slip is directly proportional to the amount of torque that the motor can provide or that is induced within the motor. And that is why it is the normal operating region. You usually have the edge of that normal operating region as your rated full load torque, and that is why we are having it at 100%. That is the point against which we measure the other torques. That is the normal torque that we would expect from this motor, right? So that is our normal operating region. Up here, we have the peak or maximum torque that the motor can give. This is maximum torque or pull-out torque. If the demand on the motor is such that it requires more torque than what is indicated here, that is, it goes beyond this point. Now, of course, the figures on the left-hand axis are relative. They will depend on the design of the motor. This is not fixed. So it doesn't mean that all motors have a 200% starting torque. That is just for purposes of an example. Or the pull-out torque is not necessarily at this point. It can vary depending on the design. But the shape of the curve will remain as this is. It can vary in kind of, it can be elongated, it can be shortened, it can be steeper, but generally there is this incline and then a sharp drop after the maximum torque. And we'll talk about maximum torque in a few minutes. The starting torque is another interesting one. You will note that the starting torque is much, much higher than the full load torque. Yeah, that means that the motor can be able to carry a load when it is starting that is greater than the actual full load, which is an advantage of this kind of motor, right? Now, because of the shape of the characteristic, you will also notice that the torque on a motor varies as the square, not the torque, sorry, the slip varies as the square of a phase voltage, but that is not directly represented by this. What is directly represented is now what happens in case we have, for example, the motor being pushed to be faster than the synchronous speed. It has already reached 0. What happens if the slip goes into now negative territory? We now have the extended torque slip characteristic, whereby you now introduce different regions of the operation of this kind of machine. So you will see a kind of reflected region down here, which is our generator region, whereby if you move or if you have a way of pushing the motor faster than what is required or what is the synchronous speed, you will then be moving into a generator region, which is whereby now you are putting in mechanical energy and you are getting out electrical energy, which is represented all the way up to double of the synchronous speed. Another interesting region is here, which we will tackle in the next lecture, is the braking region. If your slip is greater than 1, yeah, if the slip goes, changes relative to what the motor is supposed to do, we now enter what is called the braking region, because the motor is turning backwards relative to the direction of the rotating magnetic field. So what does that mean? If your rotating magnetic field is moving in one direction and the motor, the actual speed, the mechanical speed, is in a different direction, what does that mean? The field tends to drag the motor in this other direction. And that is why you have a braking effect. And that is what we say we make use of when we are braking. We'll talk a bit about that in the next lecture, whereby we make use of this effect by in order to slow down the motor even faster than how you would do it. Before that particular lecture, it might be interesting just to do a thought experiment of what would be the conditions, or how would we be able to make sure that the field and the mechanical actual rotation, the magnetic rotation and the mechanical rotation, are in opposite directions. How would you actually achieve that? So you would say in a normal operation, the field and the mechanical are moving in the same direction, albeit at different speeds, but they are in the same direction. Under braking, we have them in opposite directions. Just think about how you would be able to achieve those, right? So now moving on, let's have a look at maximum torque. How do we get the maximum torque? Now, we've said that the torque is given by this equation, which we have just derived on the other side, right? We went through and we saw how this comes about. Now, when you have the maximum torque, if we look at the Thevenin equivalent circuit, the maximum torque is obtained when you have so if we look at this, yes, if we look at this, now here we are looking at this particular element, all right? we are saying that this element represents the air gap, and in turn, it represents our induced torque, okay? So when will this be maximized? It will be maximized at a certain point when you have the power that is being transferred here is equal to, let me use a different color. So by maximum power transfer principle, the power that is being transferred here is maximum when it is equal to the power that is being transferred by all of this section, right? When these two are equal to each other, you then have maximum power being transferred, which is what we are looking at here, okay? And in turn, what is maximum torque, right? So that is the principle we are making use of when we say the maximum torque on the machine. So air gap power, we say that so we say it is maximum when the slip or the machine, the value of the slip itself is equal to the absolute total of that, okay? When these two are equivalent to each other, you have now maximum power transfer, and we are looking at which point. Remember, the characteristic is we are looking for at this particular point, right? What is the speed or what is the slip at this particular point? Because slip is what varies, the resistance remains the same. So we're looking at a variable, what is our maximum, the slip at maximum torque. So in order for us to get this absolute value, you do square root of squares, which is R Thevenin squared plus X Thevenin X2 squared, right? That will be the absolute value. So since we are looking for the slip itself, let's rearrange, and we find that it will be given by R2 over all of this, which is R Thevenin squared plus X Thevenin plus X2 squared. Okay. Now, in order for us to determine our maximum induced torque, let's do a few substitutions, all right? So we want our maximum induced torque. In order for us to make things a bit easier for ourselves, let's make two substitutions. Let's have number A, which is equal to X Thevenin plus X squared, X2. And then let's have a letter B, which is equivalent to all of this put together, which is 3V Thevenin squared, all of that the way to there. Let's call all of that as B. Okay, so B equals 3V Thevenin squared over omega C. This is just for purposes of this derivation. It is so that we kind of reduce the clutter slightly. We are able to follow what it is we're doing. So induced torque maximum will be given by this same formula here. We have B there, then we introduce A there, so it will look like B times, okay, so it is B times R2 over S, but what is S? S is given by all of that, so it is R2 over that. So when we're putting all of that in, we invert it, which will be given by all of that squared plus B squared. Remember this, that's why this is A squared, not b squared, a squared, a squared. Okay, r2 over s, which was coming from up here, right? Then divided by, now we have divided by what? R7 plus all of that stuff, R7 plus R2 over, in a similar way, R2 times R7 squared plus A squared all squared plus A, which is this one, so A squared. Okay, so the maximum, we've taken all of this and made it into B. R2 over S, we've substituted S for S max, which is given by this over here. So because you have R2 over S max becoming this, you can then erase these R2s, which are cancelling out with each other. And similarly, you erase this, cancels out with the other one. So then that gives us B times square root of R7 squared plus A squared over R7 plus square root of A squared, all of that squared plus A squared. Now, we want to get rid of the square roots. So what we do is we multiply both the top and bottom by this element. Okay. And when we do that, what then happens is we then get is equal to B times, when you multiply this by itself, you remove the square root, so it then becomes that over plus times that square root that we had talked about. Okay. Now that becomes a long expression, which when expanded out becomes B R7 squared plus A squared over the long expression Okay. Now, unfortunately, even with substitution of B and A, this is a long algebra. So now that one, we in turn factor it out so that it then becomes, once again, something a bit shorter, R7 squared plus A squared over 2 times. These two factors exist in both of them. R7 squared plus A squared times R7 plus square root of. Okay. So then what we end up with is you've cancelled that. And so we end up and we reintroduce the values of B and A. And that then becomes ultimately 3 times V squared over 2 times plus it's a long story. However, that is now the value of maximum torque, and we can highlight it accordingly. Okay. Now, one thing that this shows us is that we have the magnitude of the induced torque itself, right? Based on this, the maximum induced torque, that magnitude is dependent on, it is only dependent on these variables that you have here. However, Thevenin voltage is a fixed value. Synchronous speed is a fixed value. These are also fixed. So what this shows us is the point at which the maximum torque, or the magnitude of the maximum induced torque, is actually independent of what the slip and the rotor speed are. So it takes out, by using this expression, we have been able to take out the variables that were there, and we are able to determine what is the maximum torque that our motor can create, beyond which it will not be able to run. Remember, we said that when we have the maximum torque, it is called pull-out torque. So if we were to exceed this, the motor would not be able to run in an application. So in the event that you have an application and it requires a torque beyond this, you cannot use the motor that is in that characteristic, and you need to alter things so that you can get the characteristic that we are talking about. Okay, so that's maximum torque. So I think to wind up, it is almost there. Let's look at one example of the applications of how maximum torque and Thevenin resistance can be made use of. Okay. So we just have a look at that example. So we have a 3-phase machine. I believe this is the example we've been using even in the previous sessions. So this is an extension of what we talked about last time. So we are applying all the items that we had talked about earlier. So let's try and to wind up, let's see what we can do. So we have our motor with all these impedances, which are what we know, right? And we have been asked to find the various quantities, key of which is we want to get maximum torque and we want to get starting torque, which are useful points along the characteristic of the motor. So let's start with the Thevenin resistance, reactance, and the voltage at the same time. Okay, let's do all of them together. So from our previous equations, where was it? It was here. We have been told that the value of Thevenin impedance is given by all of that. So let's have a look at it. So the value of the Thevenin impedance is given by R1 plus JX1 into JXM over R1 plus J X1 plus Xn. Okay. And what are these values for us here? R1 is 0.75 plus J X1 is 1.2, XM is 25. R1 again 0.75 plus J 1.2 plus J 25. Okay, let's calculate that. So we have 0.75 plus, is my calculator visible? Okay. So it's 0.75 plus 0.75 plus 1.2 J times 25. Okay. Start with that. Useful on this side. Difficulty there. Okay. So it's minus 30 plus J 18.75 over, let's get the other part, which was 0.75 plus 1.2 I plus 25 I. It gives us 0.75 plus J 26.2. So dividing those two, negative 30 plus 18.75I divided by 0.75 plus 26.2I to give us that, which is our Thevenin impedance is roughly 0.6835 plus J 1.164. Now we said this is Thevenin and this is Thevenin resistance and this is Thevenin impedance. So our R Thevenin is given by that, and our J Thevenin, our reactance, is given by that. Okay. So that's the first step. Let's put it down completely. So that we have Z, it's not Z, we are looking for R Thevenin for 0.6835 ohms, and X Thevenin is equal to 1.164 ohms. V Thevenin was being given by V phase times XM over the square root of R1 squared plus X1 plus XM squared. This one was a magnitude, so we are only looking for the absolute values. Phase voltage is equal to that. You divide by the square root of 3. XM was 25 over the square root of 0.75 squared. Was that R1? Yes, R1 is 0.75 squared, and X1 plus XM. X1 is 1.2, XM is 25. So that is plus 1.2 plus 25 squared. So let's calculate that. 1.2 plus 25 equals, square that, equals plus 0.75 squared, 75 squared equals, find the square root of that. It's 26.2. Okay. So we have convert it. And then we multiply by 415 times 25 divided by square root of 3. Hopefully it gives us the answer. Yes. So Thevenin voltage is equal to 228.5 volts. Roughly. So we've gotten our Thevenin voltage and our Thevenin resistance and reactance. So now we look for the speeds. So what is the speed at maximum torque? Okay, so we said speed at maximum, we start with getting the slip. Speed at maximum was given by, come back here, the speed at maximum had been given by that. Okay, we had indicated that it is that particular configuration. So coming back to our example, it will be R2 over the square root of R Thevenin squared plus X Thevenin plus X2 squared. Okay, which for us now, R2 was 0.2, and they are similar to the ones above, so use us. So it is 0.2 over, our Thevenin was 0.6835, 0.6835 squared plus X Thevenin was 1.164, 1.164 plus X2 0.5, 0.5 all squared. Okay, so similar calculation, 1.164 square that, add it to the other one, get the square root, the inverse, 0.2. And this gives us our slip is equals 0.111. That's enough, 111. So roughly 11.1. Okay. And the mechanical speed at this slip is given by 1 minus S max times ns, which is given by 1 minus 0.111 times ns, synchronous speed, is 120 times f over p. F was, frequency was 50 hertz, and the number of poles is here, so that is 4 poles. We divide by 4. So calculating, that gives us one answer times 120 times 50 divided by 4. And that gives us a speed of 1,333 RPM. Okay. So this is our speed. What we need next is we are aiming for maximum torque, which has been the whole point of our exercise today. So maximum torque so we said maximum torque is given by what? Maximum torque was given by that expression, right? So we have calculated the Thevenin voltage, we've calculated R Thevenin and X Thevenin. We need to get synchronous angular speed. Let's start with that. So the synchronous angular speed, omega sync, is equal to 2 pi synchronous speed over 60. We are just converting from rotational to angular. So that will be 2 pi. NS was actually calculated. So let's plug it in. NS 120 times 50 over 4 times 60. And that gives us what actually we can do a bit of cancellation. And that goes into that. It's actually 50 pi. We can keep it like that. We don't need to fully calculate it. And then our T max or induced max is equal to 3 times our Thevenin voltage, 228.5 squared over what? 2 times omega sync times all that. So it is 2 times omega sync, which was 50 pi, times 0.68 to 6835 plus square root of 0.6835 squared plus x7 plus x27. This one is supposed to be out here. X2 squared. X7 was 1.164. 1.164 plus x2 is 0.5. 0.5 all squared. Okay. We calculate all that. Backwards. So that gives us a maximum induced torque of 200 and what? 0.85 roughly. 0.85 Newton meters. Right. Now there's an additional, that is our maximum induced torque. So the final question we were being asked here is the starting torque. So how do we get starting torque? So any torque at any point is given by this formula. Now, when the motor is starting at its starting point, right? It was here, okay? The speed at starting is 0. So what does that mean? It means that the speed, when we have, so let's just write it down. So we want to do starting torque. So we are saying that at start, the slip is equal to what? It is equal to ns minus 0, okay? Because the mechanical speed is 0 over ns, which means that slip is 1. Therefore, that means that our torque equation, the induced torque, this value of slip and this value of slip are equal to 1. Therefore, we can disregard them from this equation. That means we will be working this out without S. So it's a simple calculation of the values that we've been talking of. So torque at start is equal to 3 times Thevenin voltage squared, which is 228.5 squared, times R2, which is 0.2. Let's put on that. R2 is 0.2, Thevenin voltage is 228.5. Okay. Over, here's our formula again. Over that. So it's omega sync times all of those. Omega sync we had said it is 50 pi times R Thevenin plus R Thevenin 0.6835 plus R2, which was 0.2 squared, plus X Thevenin, which was I think 1.1 something, 1.164, 1.164 plus X Thevenin X2 0.5, 0.5 squared. Okay, so we calculate all of those. So we have 1.164 plus 0.5 equals squared. This is 2.7689. Then 0.6835 plus 0.2 equals squared. 0.7086. 0.7, sorry, 780. Okay, so now add those up. 0.7689 times 50 times pi, invert it, times 3 times 228.5 squared times 0.2, and that gives us the starting torque of 56.188 roughly. .188 Newton meters, right? So you can see the starting torque is much less than the induced or maximum torque. Yeah, starting torque is about 56. Maximum torque is almost 4 times as much as that. So I think we can stop